Hi everyone, in this video, we'll be doing an example of multi-dimensional orthogonality. In the orthogonality video that you've hopefully watched, you've seen how I derived orthogonality for one direction, whereas here we have a directions in x and y. And the problem that sort of arises is how do you essentially manage all your variables that kind of pop up? Like, what is essentially happening when we apply orthogonality in multiple directions? So in this problem, we're given this general solution. We're given an initial condition, and then the definition of orthogonality. So our goal in this problem is to solve for A of Nm, right? And the way we do this is by applying orthogonality techniques. So the first thing we're going to do is we're going to evaluate a time equals 0, such that we get uxy0 is equal to everything up here except e raised to the 0, because that's raised to the time. And then we equate that to the initial condition noted here, equals f of x, y. Okay, so in thinking of orthogonality, we want to multiply by some function. We want to multiply by sine of I pi x over L, and then any term where I does not equal n goes to 0. Alright, so this is the basic thinking of orthogonality. So in this, the first step I'm going to do here, I'm going to put my f of x, y on the left hand side. That's usually what I do. F of x, y, and then I'm going to multiply both sides by sine I pi x over L. Then summation m equals 1 to infinity, n equals 1 to infinity, everything else inside. So that just stays the same because all we're doing is multiplying. Times sine I pi x over L. Then I'm going to integrate both sides with respect to our boundaries, 0 to L, in order to get our problem in the form of orthogonality. In addition, there's a rule that you're allowed to switch the order of the integrands the integral and the summations, and you will not change the resulting fact. So switch those around. L, and then everything inside still stays the same, whereas we have to keep everything now because we're multiplying. Okay, so now we notice that we should look at this integral in order to apply orthogonality condition. Note that this y term, this sine m pi y over h, does not have any dependency in the integral, so therefore we can actually factor this out. So if I copy everything down again, but this time factor out the sine m pi y over h, move everything back together just to keep organized. And what relationship should pop up to you, hopefully, is the orthogonality condition from above, right? So this orange thing I'm underlining should look very similar to what we see up here. So the takeaway from this is that for that orthogonality condition, the only term that survives in this entire summation, I'm going to write this out explicitly, the only term that survives the orthogonality is when n is equal to I. For all other I where n does not equal I, a and m is equal to 0. Great. So that means we can essentially eliminate our summation now, because we're only looking at the case where n is equal to I specifically. So this leaves us only with one summation now. M equals 1 to infinity of everything that we've been just talking about. Where n is equal to I. Because remember that n does not equal I results in the integral valuing to 0. So this means we can substitute everything with I. But notice that these two functions, which I'm underlining in red right now, are the same thing. So we can consolidate them as sine squared I pi x over L. Let's bring down the left-hand side. The left-hand side doesn't really change because we don't know what f of x is. Now, all we're going to do is we're going to apply the same sort of rules that we just did. Instead of multiplying by sine I pi x over L though, we're going to multiply by, let's say, sine k pi x over L. So multiply both sides by sine k pi x over L. And our goal is to essentially do orthogonality against the sine m pi y over h. So let's multiply it on the left-hand side. Shouldn't really matter. Sine m pi y over h. Equate everything. Multiply on the left-hand side again, just to stay consistent with what I did. No, k is k pi y. This should be also k. Sorry. You'll see what I'm doing. This is why I wrote m by accident earlier. Then sine squared I pi x over L dx. Now what we're going to do is we're going to integrate both sides again. But notice that we're going in the h direction this time, so the height direction. So we're going to integrate with respect to height, in the height direction. Dy, and there should be an equal sign there. So let's add it real quick. And then integrate again. Remember that we can flop the order of the integral with respect to the summation. 0 to h dy. Cool beans. So going with the same ideas from earlier, right? What we notice here in this specific step, this specific integral right here, which is being integrated with respect to dy, is that the only surviving terms are for when k is equal to m. So going with the same thing we basically did earlier, we can ignore the summation now because we're only looking at the term where k is equal to m. So k pi y over h sine k pi y over h, where everything else stays the same. And notice what happens now. Because the sine k pi y's are the same thing, so what I'm underlining right now, you can also consolidate them into sine squared. And the same thing still stays. So on the left-hand side of things, we can simply move this integral on the inside of the dx function because it has no dependence on dx, so it's essentially just a constant, right? So the integral won't change at all. So what I'm saying here is that I can essentially just do this. Move 0 to L, so I'm still integrating with respect to x, and then sine k pi y over h, and that integral is still equivalent to the one I had above here. Equivalent. Same idea applies on the right hand side. Notice that this function, this sine function, is only dependent on y, so we can just easily move it back into the integral because a function being integrated with respect to x has no will not affect a function dependent on y. So therefore, switching out terms, we arise with, let's factor out the a and m as well. We have sine squared k pi y over h, sine squared I pi x over L dx dy. Let's just copy and paste this. And what you hopefully should see what happens now is that if we solve for a and m, which is a constant, remember that, so we basically just divide the left-hand side by the right-hand side, what we end up with is the formula that you guys more often see than not of multiple dimension orthogonality. And this is all it really is. It's nothing more than this. It's just essentially applications of orthogonality in multiple conditions. So this video was designed in such a manner to give you guys an overview on how to perform orthogonality in multiple conditions. We'll briefly overview what we did. So starting with the general solution, we noted that we have to solve for the coefficient a and m. We recall the rules of orthogonality and noticed that our goal, once again, was to solve for a and m. We multiply both sides by sine I pi x over L, which is in blue, in order to start performing the orthogonality steps. And then we integrated both sides with respect to dx from 0 to L. In moving terms, we notice this relationship come up, which is bracketed in orange. And knowing the rules of orthogonality, the only term that survives that multiplication is for when n is equal to I. So we isolate the n equals I term from the summation, and then we move on. So we do the same exact steps again now. We multiply both sides by sine k pi y over h, where our goal is to perform orthogonality against the sine m pi y over h term. And we know that in this relationship right here, the only surviving term is when k is equal to m. So therefore, we can isolate that specific term from the summation. So k equals m is the only term that survives and that's relevant. So then we drop all other terms from the summation that do not survive that multiplication. In doing so, we simplify our equation very nicely, and then we are able to get a direct relationship for a and m. Remember that n is equal to I and m is equal to k, so I could easily just write this as aik. But you may write it whatever way you want. Just make sure you state your equivalence relationships. I hope this video helped, and I hope it helps you understand 2D orthogonality to a better extent. Thanks for watching.